So one thing that we're not explicitly required to cover in the new AP Chem curriculum is organic chemistry. We don't have to learn how to name organic structures, the nomenclature for organic compounds we don't need to know, but we do need to be able to recognize Lewis structures drawn for organic compounds because they might look a little bit different, and if we're not familiar with it, it could throw off our whole understanding of a problem. But just quickly to review, an organic compound is something that usually always has carbon in it. Usually always will only see oxygen, hydrogen, or nitrogen as well. So carbon, oxygen, hydrogen, and nitrogen. Okay? And we usually refer to organic compounds as hydrocarbons. This is only if they have hydrogen and carbon in them. So you need to know that term. If a problem says a hydrocarbon, blah, 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 you need to know that means a compound that has only carbons and only hydrogens. You don't know how many of each, but you do know it only has carbons and hydrogens. So let's talk about some organic compounds. Well, let's talk about propane. Propane tank used for gas grills has the formula C3H8. So if we drew propane, how we've drawn Lewis structures in the past, we know carbon likes to bond to itself and form chains. And then each one of these hydrogens will get bonded to those carbons so that every molecule, every atom satisfies the octet rule, and boom, there's the Lewis structure of propane. Now here's the thing. Organic chemists are lazy. Drawing all those lines and all those H's, that really just takes way too much time. So they developed a much simpler, easier way to denote, to draw organic compounds that doesn't require the use of those lines and all those H's. So for example, if we were to draw propane, what we would see for propane would be a compound that looks like this. Yep, believe it or not, this structure, drawn like this, is equivalent to this in the eyes of an organic chemist. And let's talk about why. Well, the idea is every vertex, these 3 points, 1, 2, 3, represent a carbon. So in this compound, based on this drawing, we know there are 3 carbons present. Then we have to use our knowledge of chemistry. We know that carbon loves to form 4 bonds. So that means however many bonds are remaining, that's how many hydrogens are bonded to those carbons. So for example, this carbon right here, let's call it carbon 1. Okay? It has one line drawn to another carbon. So that's one bond to that carbon on the far left, carbon 1. So that means there's 3 bonds still available, meaning that there's going to be those 3 hydrogen bonds, boom, not hydrogen bonds, but bonds, covalent bonds to hydrogen, that are kind of invisible, but are assumed to be there. Same thing is true with this carbon. We'll call this carbon 3. I'm just numbering them randomly so we can keep track of them. Carbon 3. Since it has one line representing a covalent bond going to the other carbon, that means there are 3 bonds remaining. So that carbon on the end is going to have 3 hydrogens popping off of it. So if we were to draw all these in, we would have something that looks like this. And we know based on the old structure, there should be 2 hydrogens bonded to that middle carbon. Well, let's think about why that makes sense in this drawing. Well, this carbon, carbon 2 in the middle, has 1 bond coming down to the left here, 1 bond coming down here to the right, 2 bonds to other carbons, meaning it must have 2 bonds remaining that are bonded to hydrogen. Now, isn't that cool? Look how simple this is. That, what I just drew here, means the same thing as that, means C3H8. So we just need to be able to recognize that. Let's look at some other. Here's isopropyl alcohol. Isopropyl alcohol looks like this. You might kind of notice propyl kind of sounds like propane, and that means that it has 3 carbons. We don't need to know that, but this is the formula for isopropyl alcohol, the Lewis structure for isopropyl alcohol. Okay, a lot of lines, a lot of dots, etc. Well, what would it look like to an organic chemist? How would they draw it? Well, the idea is carbons become just points, lines. But what do we do now with an oxygen? Okay, well, oxygen we still draw as an O. We only draw the vertices and the ends of these lines are only represented by carbons. So we draw an O and then an H, just indicating that H is drawn and bonded to the O. You could also draw it like this. You will see both. They mean the exact same thing. One thing you will also notice, though, is that those two lone pairs up here are not drawn. It's, again, just chemists, organic chemists being lazy. They don't draw the lone pairs. It's assumed that they are there. So actually, in fact, this structure right here is the same thing as this in the eyes of an organic chemist. Well, let's think about it. Let's think about this carbon in the middle. It has one, two, three bonds going to other carbons. That means it must have one invisible bond to a hydrogen, which, oh, yep, we know that that is there. So again, if there's an oxygen in the compound, it's drawn as an oxygen. Lines are only bonds between carbons. Let's look at a third. Let's talk about benzene. Benzene has the formula C6H6. What does benzene look like? Well, benzene is a cool molecule which looks like this, with each carbon bonded to one hydrogen and double bonds between every other carbon. Okay. Well, let's see if we're getting the hang of this. How do we draw this as an organic chemist? Well, between carbons, the C's disappear. They become just vertices. So we kind of have this hexagon shape. And now we just draw an extra line inside to represent the double bond. Boom. So isn't that beautiful? Look at this. It's a beautiful structure. This represents the exact same thing as this structure here. These are equivalent. And again, if we think about like this carbon or any carbon on this ring, well, how many lines are coming out of that vertex? There's one here, two, three. So to have a total of 4 bonds, that means there must be a hydrogen bonded as well. There are 4 practice problems. I want you to go ahead and give these a shot, so try pausing the video after I draw the basic structure. You can go ahead and try doing without me drawing the basic structure first. That would be more of a challenge that you could push yourself to do. But here is the basic structure for C4H10. Here's the basic structure for CH3OH, methanol. And here is CH3OH. So go ahead for practice, take these 3 compounds and draw them as an organic chemist would. And I'll show the results on the next page. So hit pause to give a practice. Okay, so what would your answers look like? Well, for C4H10, boom, there you're done. 1, 2, 3, 4 carbons. You don't even need to have the numbers. That's just to help with naming. So, boom, just to look at it again, final answer would look like that. Notice the reason it's drawn at a kind of an angle like this, because we know that the bond angle is going to be tetrahedral shapes. It's going to have 109.5 degrees. So this kind of represents the geometry as well. So a structure that looks like this is not really geometrically accurate. C3H10, CH3OH, excuse me, would look like this. Kind of a weird one. And CH3COOH would look like this. There you go. So we just have to be able to recognize these structures in problems. We don't necessarily have to be able to name anything, but being comfortable with, yep, this is the same as, with a C out here and three H's, and this represents a C, etc., is a skill we need to have.